right, welcome to the stage, the moderator of this session and the founder and CEO of Bennett AI, Kathy Cahalan. Welcome.
Great, thanks, Lucian. Hello, everyone, and welcome. I'm Kathy Cahalan from Bennett AI, and I'm excited to be moderating this panel discussion, AI-powered predictive analytics driving profitability through proactive maintenance. I'm joined by industry experts from Influx Data, Honeywell, and Omdia, and we have a packed session as we discover how time series data technology empowers manufacturers to leverage AI for predictive maintenance. In this session, you will learn how to use real-time data to anticipate equipment failures, optimize maintenance schedules, reduce downtime. You will gain insights into how companies have extended equipment lifespans and lowered operational costs, providing you with actionable strategies to enhance efficiency and profitability in your operations. So before I start, I want to take a moment to ensure everyone is acquainted with webinar tools and go through a couple housekeeping items. So first, if you can look around your screen and look for the chat function, it should be over in the top right-hand corner. And if you let us know in the chat where you're located, we're really glad to have you. I see we have Raja from India, we have Salona from Houston, and Ramirno from Barcelona, Spain. So we have quite a dynamic group with us. So thank you again for joining. Now, if you can look beside the chat button and you will see the queue for questions and answers. This tool is where you're actually going to post any questions for the panelists that you have, not in the chat. This is only because it'll allow us to be able to moderate the questions better and so that we can help get to more of the questions and answer them. We have set aside time at the end to answer questions, but if your question has not been answered, I've been assured by the IIoT world team that they will provide a follow-up. So please just ask away. I also want to make you aware of a couple upcoming IoT World events to mark for your calendar. So October 14th is IoT World ICS Cybersecurity Day. And December 4th and 5th is IoT World Manufacturing and Supply Chain Day. So just a reminder for our session, it will run for 59 minutes and it'll leave you enough time to get to your next session, which is AI-driven process optimization, achieving faster turnarounds and higher margins. So on behalf of myself, the panelists, and IoT World, we want to express our sincere gratitude to all the sponsors for their support in making this virtual conference possible. And an extra shout out to Influx Data, who is our session sponsor. So thanks for the contribution. It's greatly appreciated. So at this point, I'd like to introduce you to our esteemed panelists, and I'm going to ask them each to just tell you a little bit about themselves and their companies. So I'd like to start with David Sprogis, who is the Senior Technical Product Manager at Influx Data.
Thanks, Kathy, and good day, everyone. I'm a software engineer turned product manager. Yes, one of those. I wrote code for about 20 years. Most of the software that I developed was involved with databases and analytics in some form or another. And I have both Sybase and Vertica on my resume, but I've been with Influx now for almost a year and loving the time series thing. Back to you, Kathy.
Great. Thank you so much, David. Deepika. So Deepika Sandeep is Director of AI and Honeywell. If you could introduce yourself, please.
Sure. Hello, everyone. Thanks for tuning in to this session. I'm Deepika. I lead the AI function for Honeywell's Building Automation Business Unit. So here we leverage AI for sustainability, automation, and optimization of operations in commercial buildings. I also lead a community of practice for generative AI for operationalizing this technology at scale. And outside of work, I mentor early stage startups and new entrants in the field of data science. Glad to be part of this panel today. Thanks for having me. Back to you, Kathy.
Glad to have you, Deepika. So next we have Alex West, who is the Senior Principal Analyst, Industrial IoT at Omdia.
Thanks, Catherine. So yeah, hello everyone. I'm Alex West. So I lead industrial sustainability research at Omdia. Prior to that, I led our digital transformation in industrial IoT research at Omdia, which is a leading technology, market intelligence and consulting firm. So really a lot of my role is looking at that intersection of digital transformation, in manufacturing. So what are the applications that are being used? How are they evolving? Who are the players? What is that voice of the customer in terms of adoption? And so one of the areas that we've spent a lot of time looking at is predictive maintenance and asset monitoring.
Wonderful. Well, this is going to be a great session. We're going to break the discussion down into 3 sections. So the first one's going to be an introduction to AI-powered predictive analytics. Then we'll go on to applicable insights and best practices, and we'll wrap up with addressing challenges and future discussions. And as I said, we'll be able to take some questions at the end of the discussion. So let's begin with an introduction to AI-powered predictive analytics. And David, if I can ask you to kick the session off, if you can give us a little overview of AI-powered predictive analytics, specifically in the context of manufacturing and how it's reshaping manufacturing strategies.
Happy to. Thank you, Kathy. AI-powered predictive analytics in manufacturing leverages machine learning algorithms and data analytics to anticipate equipment failures before they occur. By analyzing data from sensors and environmental conditions, these models can predict when a machine is likely to fail or require maintenance. This approach shifts maintenance strategies from reactive, fixing things after they've broken, to predictive, before they break, which is much more efficient and cost-effective. The benefits include increased equipment uptime. By predicting failures in advance, manufacturers can schedule maintenance during non-peak times, reducing the downtime and keeping production running smoothly. Another benefit is cost reduction. Predictive maintenance minimizes unplanned downtime, which can be costly due to halted production and emergency repairs. 2 trends in predictive maintenance have influenced the products we build at Influx: increased sampling frequency and increased data precision. And the reason is obvious. Increased frequency and precision improve model accuracy. But these increases drive up data volumes and cardinality, which can be challenging for a database. Bigger volumes and higher cardinality were fundamental requirements in shaping our Gen 3 product line. Kathy?
Okay, great. Thank you so much, David. So I'd like to open the discussion up now for everyone. So I'd like to start with a question which is about what are some of the key challenges manufacturers face when implementing AI-powered predictive analytics, and how can these be overcome? So Alex, can you start with that?
Sure, thanks, Kathy. So I think when we think about AI technology, that's really the cherry on the top in terms of all the things underneath it that are needed to make it, to enable it. And so a couple of the key enablers that we see are around data and people. So the AI is nice at the top, but it's the things underneath it that are going to really make it work. We did a study a few years ago and found that 2 of the 3 biggest challenges to digital transformation were just around, can companies collect the data, and when they do have the data, how do they get anything meaningful from that? So just kind of doubling down on that a little bit, when we think of data, that one of the issues is just, can you get access to the data, especially in the industrial environment? There's lots of legacy assets, and there's also legacy approaches. You know, the traditional approach to maintenance reliability is to have someone on a scheduled route-based approach. So they're going around asset by asset, collecting information manually. That could be entering it onto a portable device or even putting it onto paper. At the same time, you've got, as well as that access to data, you've got issues around quality. Now, some people may be familiar with the saying, data is the new oil. I think that's really even more accurate than maybe it was meant to be, because in the same way, you know, vehicles, if you fill the vehicle with oil, it's going to break. You need a refined product, gasoline, to make it run. In the same way, if you're going to use data to support your organization and help decision making, that really needs to be cleansed, contextualized to give it some meaning. So in terms of that side of things, I think there's challenges around just standardizing data, naming formats of data, that dealing with issues of siloing data. And then the other side of it is the people. You know, are people willing to use the technology? There's sort of the picture of the old reliability engineer going around the plant, placing a screwdriver on the motor, putting his ear to the screwdriver, listening to the vibrations of the motor and using that to make a decision. Now, when you put a predictive maintenance solution in front of him, a lot more technological, he's got to trust the data first and foremost. And that can be a big challenge in just getting to trust and work with it. They've got to see, he or she, has got to also maybe go through some of that extra effort to learn a new approach. And especially when you're talking about an aging workforce or a workforce that's about to retire, there can sometimes be that resistance to learning new approaches. And also they've got to understand that if I'm going to work with this new technology, ultimately it's not going to be replacing me. So there's that fear of technology as a threat to their job. So really trying to position these technologies as augmenters to the work that people are doing rather than a replacement. So back to you, Kathy.
Absolutely agree to that part. So thank you. So Deepika, this question is for you. Can you explain for everybody how real-time data analysis differs from other data analysis methods in terms of the outcome and the value that it adds in terms of impacting equipment maintenance schedules and operation efficiencies?
Sure. Thanks, Kathy. So, real-time data analysis is different from a data collection and an infrastructure requirement standpoint as compared to other data analysis methods that use batch processing. So, let's consider the context of a digital twin. So, this uses streaming data to analyze and visualize the asset status in real time as it operates. It enables operators to remotely monitor and also control various parameters of equipment. So, the value that a digital twin brings is being able to catch abnormalities in real time and provide just in time maintenance recommendations for maximizing the throughput, extending the asset health, and also bringing about energy efficiency, which is critical in today's world. So, as an example, say an HVAC system, a heating, ventilation, air conditioning system, may be clogged, but it'll still run, it'll still operate. It will, however, consume more energy than it is supposed to. So, this is an ineffective way of operating it. And in these kind of scenarios, real time data analysis solutions go a long way in spotting these inefficiencies and driving actionable outcomes for energy efficiency. Also, another energy conservation measure is equipment schedule optimization based on the real-time occupancy and usage patterns in a building. So now switching context a little bit, say in a utility scale solar farm, for instance, string disconnections and soiling of the solar modules, which is nothing but dust accumulation on the solar modules, are common phenomena, and they bring down the energy generation capacity considerably of the assets. Hence, real-time data analysis is necessary to identify these anomalies as and when they occur and take corrective action. So that's how predictive analytics brings in a lot of value. Back to you, Kathy.
Great, thank you. So just sort of extending with this, so David, can you tell us a little about how time series data and time series database technology specifically enhances AI's capability for predictive maintenance?
You bet. First, time series databases such as InfluxDB are optimized to store, query, and analyze time series data efficiently. This is crucial given the typically high volume and velocity of data. Second, time series databases are designed to analyze data in real time because the sooner that you can detect a problem or an opportunity, the more quickly you can take action. In a production environment, this could, for example, mean making minor adjustments to extend the life of a component until it can be replaced. Third, as I mentioned earlier, increased precision and sampling rates contribute to better model accuracy, which gives you confidence in its predictions. This can help you make better decisions when replacing expensive parts. Time series databases come with built-in functions for downsampling, aggregation, and transformation, which are critical in preparing the data for AI, something that Alex touched on earlier. These functions accelerate pre-processing, such as removing noise, filling gaps, and extracting meaningful features that improve AI model performance. The general goals are always to have the data ready before you need it and process as much as possible in the database so that you're moving as little data as possible over the wire, and compress data so that it's smaller on the wire and more efficient at rest. Kathy?
Great. I have to say, as a person who was a frontline worker for 5 years, the ability to very efficiently know when to take a machine down, have parts ready, just respond as need, would have made my life so much easier and my entire crew. So this discussion in on predictive maintenance always really resonates with me and excites me. So thank you for that. So we're going to switch the conversation over to applicable insights and best practices. So my next question is a two-part question. It's for you, Topeka. I'd like to start. What are some of the best practices for ensuring data quality and accuracy when dealing with vast amounts of data? And then the second part is, how do we collect this data?
Sure. At Honeywell, we work with a lot of real-time IoT data collected from various sensors, and this is typically very noisy. And some of the best practices we adopt for processing this data are as defined by the industry standard CRISP-DM framework. It starts with a robust data collection and ingestion. Communication breakdowns are quite common in the IoT world, so we need a mechanism for buffer storage in the gateway. Wherever possible, we employ edge analytics to reduce latency. The foundation for any data-driven solution is a robust end-to-end data pipeline to handle ingestion, storage, and extraction from different sources of data. The raw data, typically IoT data, requires a lot of cleansing, pre-processing, outlier detection, and treatment for the data quality to be right for the algorithms to analyze or learn from. So a couple of metrics that determine the quality are bias and variance. And we also automate the testing and evaluation as much as possible. MLOps practices post-deployment ensure that the effects of data drifts, model drifts are minimized. And another important aspect while dealing with vast amounts of data is parallel processing. A key consideration is computational complexity. Many data analytic solutions using deep learning methods specifically undergo quantization to become compatible and to be able to run on IoT devices with limited computational capability. And this optimization process often becomes a game changer in real world edge deployment scenarios. So all these enable value addition from real-time data analysis on streaming data. Yeah, Kathy?
Okay, great. Thank you for those insights. So building on the topic of data management, let's shift our focus to manufacturers using AI to drive real world results. So this question I'd like to ask each of you and to take an opportunity to share a successful use case where manufacturers leverage AI-powered predictive analytics to improve profitability and overall operations. So Alex, can we start with you?
Sure. I think the good news is there's a lot of applications that we're seeing coming up utilizing AI. So, and they're coming out every day. But I think beyond the use of specifically to maintenance, I'd highlight, one of my personal areas of focus is around sustainability, and it's tying in that use of AI for energy management applications. So obviously with all the regulations that are starting to come out and soon to be mandated, this is becoming increasingly important. It's really sitting on the C-suite level as well in terms of their focus, but it's not just a regulations issue, it's certainly a cost and profitability issue. If you think of an energy intensive industry like the chemical industry, I think their energy is the second largest operational cost after feedstock. So you're talking a significant portion of their cost is coming from energy. And so really utilizing analytics to, as a starting point, get a benchmark of, which are my energy consuming assets, where are my good and bad players, and really identifying that, and then being able off the back of that to start doing things like forecasting energy drift, which is sort of unexpected changes and increases energy consumption. Can be used for also tying into that energy side, forecasting future energy consumption patterns, and that can be both allowing you to adjust your production, but to sort of balance energy consumption, but also in terms of looking at the balance of your energy mix. So how much of my energy is coming from traditional sources versus renewable energy sources, for example. And this you can really start planning down in hours and days in advance to optimize your plans. I think one other example tied to that, and then when you're extending out to the grid, is that prediction, prevention of what's called coincident peaks. And coincident peaks are when there's multiple users all trying to use energy at the same time. That creates a higher price of electricity or energy, and you can then adjust your consumption accordingly. And then just as a final, tying it back to predictive maintenance, simply, if you stop a downtime, then you don't have to have a restart, and a restart can use a substantially more, there can be a delta in the amount of energy you're using just to get your processes restarted again.
Absolutely. David.
Sure. I'm going to call out Olympus Controls, who we've worked closely with. Olympus helps their customers eliminate unplanned downtime with many of the things that I've mentioned already: better early detection, more sensors, increased sampling frequency, more model features, and ultimately more accurate predictions. Higher data volumes and higher cardinality drove development of our Gen 3 architecture and really backs the kind of analysis that they're doing with their customers. An obvious goal is to schedule replacement before failure. Sometimes that requires throttling some systems down, again, to reduce stress until they can be repaired or replaced. These steps help minimize planned downtime and ensure that the parts and labor converge for faster, more efficient maintenance and reduced overall downtime. Kathy?
Okay, great. Thank you. And Deepika.
Yeah, so like Alex described, a mega trend that we, Honeywell, also as an organization are focusing on is sustainability, and we leverage AI extensively to build and deploy energy conservation measures in commercial buildings, and also measure the impact through energy baselining. So, in simple terms, the energy baseline is an estimate of the amount of energy a building is expected to consume given its current operational conditions, as in the occupancy, temperature, humidity, air quality, etc. So, the baseline value is predicted based on these parameters and is then compared against the actual energy consumption as recorded by the meters. And if the actual value is drastically higher than the baseline, root cause analysis is undertaken to identify which equipment is consuming more and why. And this energy baseline process helps quantify the value in terms of energy savings from each energy conservation measure we deploy, and also optimizes the overall operations. Kathy?
Okay, thank you. So thanks for sharing impactful use case, which I'm sure everyone's taking a lot from and has a lot of ideas. We do have a question. I'm going to bring it at the end of the discussion because it impacts more overall what we've been talking about so far. So now that we've explored best practices and successful implementations, let's dive deeper into how AI-powered tools are influencing day-to-day operations. So David, could you walk us through how predictive maintenance powered by AI influences the decision-making process within manufacturing operations?
Yeah, you bet. Predictive maintenance is about risk reduction. How will you maximize your yield while lowering potential costs? And for each prediction, you want to make sure parts and experts are prioritized and scheduled to be effectual. Your first focus area should probably be proactive maintenance scheduling. As I think I mentioned earlier, predictive maintenance allows decision makers to transition from reactive to proactive maintenance. And being proactive about a maintenance schedule, I think, is top of your list. The next area should probably be resource allocation. Maintenance teams can be deployed strategically. Tools and parts can be ordered just in time. Also, maintenance budgets can be optimized based on predictive insights. Another area of focus is continuous improvement and optimization. I think this plays strongly into Alex's point earlier that there are a bunch of steps along the journey to predictive maintenance, and all of it is aimed at continuous improvement and optimization. You can't improve what you don't measure. I should be able to tell you who said that, but I can't remember. In any event, it's important to measure and continuously analyze the flow of data for ongoing process improvements. Kathy?
Okay, great. So Deepika, back to you. What are some of the ways that companies can integrate AI-powered predictive analytics into existing maintenance systems without major disruptions?
Sure. So digital transformation and sound data infrastructure are the key to successful AI-powered predictive analytics. AI is not just about building the algorithm, it needs an ecosystem of data collection, be it streaming or batch, a data warehouse, ETL process, which is extract, transform, load, the serving infrastructure, monitoring, and ops. So companies first need to invest in building this data ecosystem and then build AI systems on top of it. And data from myriad sources, structured and unstructured data, as maintenance records, operational data, metadata, all come together to build and integrate predictive maintenance solutions. So, for instance, in the commercial buildings context, we encounter scenarios where additional sensors or instrumentation is required to collect data in order to analyze and bring about energy savings as an outcome. But the design of many buildings does not even support or accommodate installation of any additional instrumentation. So in these cases, we use existing data to estimate the remaining data parameters through machine learning methods, which would otherwise require a physical sensor to record data. So such software-defined estimation solutions are examples where data-driven solutions themselves can in turn minimize disruption. Kathy?
Okay, great. So this brings us to our final topic, which is addressing challenges and future directions. So let's jump right in. So I'd like to ask each of you, starting with Alex, what common misconceptions have you encountered and how do you address them?
I think the first is, hey, I've got a silver bullet. This has fixed all my problems. So, that idea that once you've got predictive maintenance, that's the end of downtime. In reality, this is not a catch-all. It's not 100% accurate. This is not a perfect solution. Firstly, you're not going to use it everywhere. It's not cost-effective to place predictive maintenance solutions and sensing and everything across all of your assets. You're really going to go through an asset criticality assessment, really identify which are your priority assets, which are the ones you really need to track because they're critical to your process or they're particularly high cost items. Think of a light bulb. You operate a break fix approach. If it breaks, you fix it. There's going to be assets that you have that approach. So I think point one is it's not everywhere. There's also, the models are trained on historic data. You're going to get new faults where the model hasn't been trained on it because that wasn't in the training data. So again, it's going to be going back to David's point, it's continuous improvement. The models are going to continuously improve over time as well. And so you are going to have some faults. And this goes back to points Deepika made and I made earlier, that the quality of data is going to be an issue that may introduce faults. You've got to get your people to use it and to trust it. And that's going to be key as well. So I think in terms of recommendation, it's have a realistic expectation and a real learning mindset but you can't just switch. Right, that's the end of my maintenance and reliability team. It's really an augmenter, not a replacement to your workforce.
Okay. David.
Yeah, I'd have to concur with Alex, and this is going to sound a bit like a theme, but I'd have to say that the biggest misconception relates to the number of steps involved with ramping up a predictive maintenance solution. You need to get the data, and you need to get the right data. Older equipment may not be throwing off the signals that you need to accurately predict failures. I recommend interviewing the most tenured operators on the floor. They're going to know what to look for and possibly give you insights into how to collect that data. If you are collecting data, you still need outcomes, failures, to train the models, as Alex indicated. And it takes time to collect enough data to train the models. During this data collection step, it makes a lot of sense to present the data to everyone to see. So create dashboards, establish KPI, share it broadly so that the organization is on board with data-driven decision-making. And then once you have sufficient data to train the models, bring them online as advisors and add the predictions to your dashboards and sanity check them with those most tenured operators that I mentioned in the first step. There is no shortcut to this process, and you shouldn't rush it. You're not only making a technology change, but you're making organizational changes as well. Kathy?
Absolutely. So Deepika.
Sure. Predictive maintenance has many benefits like optimizing operations, asset life extension, saving cost, etc. But it cannot avert every failure. It provides early warnings of failures, which may help avert failures in some cases, and in others provide leeway to prepare for the failure. It could be mobilizing components if replacement is required or repairing components as necessary. Also, a predictive maintenance solution cannot predict failure if there is absolutely no sign of any degradation or anomaly. All that it does is spot inefficiencies, anomalies as soon as they occur, provide an estimate of the remaining useful life, and provide corrective action recommendation to minimize the damage. Also, this is more of a recommendation system. The action needs to be taken in a timely manner for us to be able to realize value from such a solution. Kathy.
Okay. So this is our last group questions to everybody again. We actually have quite a few questions in the question and answer section I'd like to get to. So starting with David, this question is looking towards the future. How do you see the role of AI in predictive maintenance and how it evolves? And what should company do to prepare for these challenges?
I think we all wish we'd have that crystal ball to know what the future is going to bring. Seriously, predictive maintenance will blend into fully automated operations at some point. I think the sky is the limit, as they say. AI will continue to replace humans as it gets smarter until there are no more humans in the loop. I don't know when that'll happen, but I'm pretty sure it will. And at some point, AI will improve the AI itself, but that's the stuff of science fiction. How should companies prepare? Well, start now if you haven't already, and always plan a couple of years ahead. I would say be aggressive, but remember again that there aren't any shortcuts. Kathy?
Okay, great. Alex?
Yeah, I think where I see it, and again, this is future, as David said, but where I'm really excited as seeing the opportunity is really where you start tying the data from predictive maintenance alongside other applications to get this really holistic picture from an overall business perspective. You know, one of the big challenges with data and everything across, not just data, people, everything across an organization is that siloing. You know, we're working on a project in our department, the data doesn't flow, or it's a different format, or we're not sharing. But if you can get that break those silos down, start standardizing data, get different systems integrated and talking to each other. Start thinking about, for example, I see something really simple, like through predictive maintenance, I can identify there's wear on the tooth of a gearbox or imbalance on the rotor of my motor. I can now identify future failure. Now I can use this to feed into my reliability and maintenance team to, through something like a CMMS, a computerized maintenance management system. I can adjust work schedules. I can optimize their time so that they're just focusing on the assets that are degrading rather than just checking my whole asset fleet. I can start looking, and this is something that some tech vendors are already supporting. But beyond that, I can start making other decisions that impact other departments. A faulty bearing on a motor could start impacting the quality of a product that's being produced. Now that starts impacting my quality team. It can start tying into my operations, my supply chain, customer relationships, finance, HR, all of this, because there's different departments are impacted. So as you get this data and context, now I can understand, taking another example, I can see which orders are coming in, when they need to be fulfilled. If I'm seeing a potential downtime, now I can identify, well, what's the availability of spare parts from the supplier? Do I have the engineers with the right skills in the right places? And then, of course, what's the impact? If my asset hasn't failed, but it's degrading, is that starting to cost me more energy? Now, as I start getting this information, I start making adjustments. I can prioritize, do I need to turn off a certain line to avoid downtime, or do I keep it running at a lower throughput rate? Or do I have an order that I have to make? And if that means running to failure, I'm willing to take that risk because financially it makes sense. So, at the moment, most AI projects, they're sitting in a little silo. In that silo, you can see if it's successful or not. You're not able to see that overall picture. What does this mean for the business as a whole when I consider all the different departments? I consider the bottom line of the organization. So as people start bringing that together, and that's not happening tomorrow, that's still a long way away, that's where it gets very exciting. And then you can even start thinking, and this goes back to David's point, now you can start maybe closing the loop, automating some of this. You set the parameters and the processes are optimized accordingly. So I think that's where it's going, but yeah, this is a longer term plan, I think.
Great. Deepika.
Yeah, so now with generative AI adoption gaining momentum, AI powered assistants are being extensively developed for predictive maintenance. For them to be able to drive the desired value, digitalization is key. Many a time we have found availability of comprehensive maintenance data to be a challenge in the predictive maintenance context. Maintenance data collection and storage, metadata in terms of asset map creation and keeping it up to date are essential for AI models to be able to learn from large, diverse data sets and be able to effectively provide assistance. So, in essence, AI has the power to change calendar based maintenance to condition based maintenance, but it all starts with data. Hence, a robust data strategy is the foundation for a powerful AI strategy.
Great.
Yeah, Kathy?
So this ends this part of our discussion where we established our questions that we wanted to answer. I have some questions from the audience. They aren't directed at anyone specific, so anyone that wants to jump in and take a go at, and then everyone else add in, please. So let's start with Benita asked, how can turnaround shutdown teams start using their data, and who should champion this and get budget from the above? Anyone?
So I think before we jump into a solution, it's important to understand what is the problem that we are solving and why it is important to be solved. So what are those, who are those end users? What personas do they belong to? And then probably even understand the data first, even before we use or analyze the data for any predictive maintenance solution, because the data experts and the domain experts have to come together, and the data experts have to understand what data they are working with in order to create any solution using that data. So that would be the first step, I would say.
Okay. Does anyone else want to add?
I would add, just get started. You know, there's that paralysis by analysis. Like, oh, how are we going to do? You know, you can get the basics started, start collecting data. I think you've got a mix of solutions. You've got some that are very in-depth and you're going to get quite complicated. I think there are others where, you know, there's a low cost of entry to start collecting data. And there's some of these sort of end-to-end systems almost that you can start working with. So I think one of them is just get started. I would throw in a little bit of caution as well around, sometimes people sort of champion that POC, that proof of concept, and you can get drowned with these proof of concept projects that really don't provide the full, you know, this is a real benefit. It's a little project. It shows a little bit of benefit. It doesn't really show the value of a real significant investment. And so sometimes you have to take a step back, look at a strategy. So we're not going to run this on just one little motor sitting on the corner of our factory, for example. We're going to give this a try and really sort of dive in. So I think there is a part of just diving into the deep end and getting started.
Okay. So Ashika asked a question. First, she wanted to thank all of you for your insightful contributions. Her question was, failure events are rare compared to normal operations, leading into an imbalanced data sets. How would you suggest we overcome the challenges of this imbalanced data sets? And could we potentially miss out on something by oversampling or undersampling?
Yeah, I could probably start. So we do see in all maintenance records that it's not a perfect failure that we get data for. So like Ashika is saying, that failure events are quite rare. So the approach that we take in order to train the machine learning models or the AI models is that we train them on the normal behavior, right? So for that, we have ample amount of data. So we train them to learn the normal behavior. So once they have learned the normal behavior, any abnormal behavior which is different from what they have seen in the past, the models would trigger as an anomaly. So that's how they are able to catch anything that is away from normal. So the approach that we take is to train them to learn the normal behavior rather than each failure, which is very rare to get in any maintenance data.
Okay.
Think of the Bank of England, how they check for money laundering is they don't check lots of fakes. They get their people to check lots of real versions. And by knowing the real version really well, that identifies when there's a fake. Someone will know there's something different. And I think to Deepika's point, you know what the basis is. I think, as I mentioned earlier, you're going to get failures. It's part of the learning process. It's not 100%, and it's a learning process over time. So you accept there are going to be some failures. As you collect more of this data, that sample collects more potential failure causes and builds a stronger data set over time.
I'm going to, if you don't mind, yeah, I'm just going to amplify something that Alex and Deepika both alluded to earlier. And that is the notion of normal operations. I mean, I read this question and I see normal operations, but is there really such a thing as normal? Bearings are going to wear down over time, and at the same time, you might be predicting when they might fail. You may not want to wait that long. And I think this is something that Alex specifically said, which is you may want to lubricate those bearings long before failure. So more broadly, if you look at the problem, it's predictive maintenance, but it's not just looking for failures, it's looking for opportunities to maintain. And so don't wait for it to fail, right? Jump in and oil those parts. Catherine.
Okay. So this question comes back to the proof of concept. Alex, you talked on it a little bit. The question is, can you give an example of a successful proof of concept for a predictive maintenance project? How much time did it take? what was the burden on the maintenance supervisors and workers, and what was the actual savings versus predicted savings, if you are able to answer that part.
Was that to Alex?
That's actually, it's open. I was just saying that Alex sort of touched on it, but David, if you have an example, please go ahead.
Yeah, I mean, I'm struggling a little bit with the concept of a POC for a predictive maintenance system when, I believe in my heart you got to be all in on this, and that starts with collecting the data long before you get to the predictive maintenance. Alex said it earlier, be strategic about what you're collecting and what you're collecting it for. You probably don't want to measure light bulb lights, but maybe the more expensive equipment and more sensitive equipment. I'm aware of a project that was not specifically an operation, but it was products that are very high-end imaging products as medical devices, and downtime of those medical devices was very expensive, not only in financial sense, but also in health sense. When that imaging equipment is not available, people are not getting the diagnoses that they need. And that was a very long process, first in instrumenting the equipment, second in collecting the data in an actionable kind of a way, and then building the predictive models on top of it. I'd say it was a 6-year effort, end to end, 2 years, 2 years, and 2 years, something like that. Alex, Deepika?
I don't have a specific project, even maybe I'm kind of meandering slightly away from the question itself, but I would say just consider also in terms of is it a success or what's the payback? Kind of depends on whose perspective. Like we found a lot of times if your IT department's involved, they generally have a far quicker expectation on ROI than operations and maintenance. So there's that to consider. Managing expectations, but also that in general we see these sort of projects underperform expectations in the short term and then overperform in the long term. Again, that's partly as a result of these models get better over time and they improve over time, the people use it better and things like that. But just in terms of that idea of getting started, just a few thoughts, Marsha.
So I could probably add about an example of a predictive maintenance solution that we built for wind turbine maintenance. So this was for predicting any gearbox failure, any specific component failure of a wind turbine. So in this context, we required about 1 year of data at the minimum because all the weather patterns had to be taken care of. So in order to collect that data itself took us a year, and then building the solution on top of it was probably a couple of months effort, but the major effort goes in the data collection and the pre-processing of the data and the whole ETL process from it.
Great. So David, as we're talking about this, are there specific tools and technologies, for example, from Influx data that you would recommend for a company just starting out with their predictive maintenance journey?
That sounds like an offer to advertise some product from InfluxDB. InfluxDB
From the others, yeah.
InfluxDB is optimized for high throughput writes and is capable of managing millions of high cardinality data points per second, which is crucial for predictive maintenance where real-time data from sensors is continuously ingested. It also offers flexible query capabilities, allowing users to easily extract insights from the data. Another product that we have is Telegraph. Telegraph is an open source server agent for collecting and reporting metrics. It simplifies the process of connecting data sources to InfluxDB and supports over 200 plugins for various input and output sources. It streams this data directly into InfluxDB, enabling real-time monitoring and analysis. Telegraph's flexibility and ease of setup make it ideal for companies starting with predictive maintenance. Chronograph is the user interface for influx data platforms, provides visualizations, dashboards, and administrative capabilities. Chronograph enables users to quickly set up dashboards for visualizing data collected from Telegraph and to store it in InfluxDB. Chronograph is a great way to include and involve your operations team in data gathering and data-driven decision-making. Capacitor is a real-time streaming data processing engine that can be used to trigger alerts, detect anomalies, and perform actions based on data stored in InfluxDB. We've been discussing predictive maintenance, which should not require real-time analysis, but things still do break, as Alex pointed out with his light bulb example. And when they do break, you want to know right away. Kathy?
Okay, great. Alex, Deepika, are there tools that you guys use in your organization that sort of comes to mind? I am looking at a question that was asked, and let me know if this doesn't tie in specifically the way that I'm thinking it does. But they were asking if you could also explain a few machine learning algorithms that are used in predictive maintenance and how this decision making to pick that particular one is used, and how is it trained on historical data and how many data failures. There's a lot in this question. I'm hoping you guys might be seeing it, but it'd be great if we could touch in what your guys' individual experiences at your companies are, as well as helping this person.
To you, Deepika. You're happy to.
Yeah, go ahead, Alex. Yeah.
No, I said I'll defer to you. Go for it if you're happy to lead.
Okay. So when it comes to the choice of the algorithms, I think we are spoiled for choice, and it's all dependent on the complexity of the data that we are dealing with. A simple regression algorithm could solve the problem, but if the complexity is high, then we may want to go with something like a deep learning or any neural network kind of machine learning algorithm. So it is about how the data fit, how the model fits the data. So that's what determines which model to use. And today we have a lot of AutoML tools which tell you which is the best fit for that particular data. So it's a library that can tell you help you with the decision making on the right ML algorithm. And yes, it is trained on historical data. And like I said, if it is dependent on weather, which typically it would be, then we would need all weather patterns to be covered in the data and ensure that it is representative enough. And how many data failure events from the past does it need? As many as available, I would say, but it is hard to get failure data. So like I initially said, we train on the normal behavior rather than look at all possible failure scenarios because it is very difficult to get exhaustive data for failure.
Okay. Alex, do you have anything else to add? Okay. So the question just came in. Let's see. It says, what challenges will a predictive maintenance system face when implemented in legacy industrial infrastructures?
Yeah, that's a great question. I'll take a quick whack at it. So the medical device imaging company that I mentioned earlier did have this situation. They had older equipment that was still very functional, but was not instrumented with sensors, and so they had to re-outfit that equipment with sensors in order to collect the necessary data, in order to begin to think about even creating a predictive maintenance solution for it. So, I mean, the answer really is do the best that you can. Try to learn from the experts. Whether it's highly tenured operation personnel, or it's field maintenance people who see these failed devices all the time, and they're the ones who can give you insights to get started in what kind of sensors you might want to put on the older equipment.
Okay, so that ties another question I think we've touched on a bit, but maybe just to answer it very specifically is, what are the specific data pre-processing steps that are necessary for optimizing AI models? Any takers on that?
Well, okay, I'll venture that, you know, one of the first things you want to do is normalize your data, right? And so normalization could be putting it on a scale from 0 to 100 or something like that. Other things that you might want to do, Alex alluded to it earlier, is to fill gaps and rinse out some of the noise that might be in your system. Alex, Deepika, anything else you want to add?
AI tools now that are being used for cleansing data as well, right? So there's also tools to improve that quality of your data, but even things like sort of common naming formats. So you've got the context, you know, how do you write something, you know, is it plural, is it abbreviated? And so you could have 10, 15 naming formats of exactly the same thing. So just standardizing that across an organization, because again, lots of people are working in silos, different ways of working, never had to never had to work across an organization before. So I think there's some sort of standard data practice approaches that can be used.
Yeah, and also the definition of outliers can change with the data context itself, right? So it is extremely important to have the marriage between the data experts and the domain experts, because the domain experts understand data like nobody else. And given their wealth of experience with that data, I think predictive maintenance solutions should leverage their experience as well.
Okay, perfect. So we have about a minute and a half left. So there's a question from a student that I would like to bring forward. And oops, I'm getting all the little pop-ups that I'm sure everyone else just did about rating how the session was. So this question says, as a student of architectural environment engineering in the UK, the use of predictive AI for building management is not becoming more common. However, construction industry is still very slow in the uptake of this technology. How can we promote this technology further? So probably only have time for one person to provide some input on that.
Deepika, I think that's you. You've mentioned HVAC systems.
Yeah. So, when it comes to construction industry, so what would make more sense in that context would be something like a generative design. So we have a lot of architectural design that we do in the construction industry, and predictive analytics or AI specifically can add more value in the context of generative design there. And in any greenfield project, it is absolutely necessary to design the sensors. And the kind of use cases that we have is finding the right places where these sensors have to be installed. So otherwise, it is a very manual process today, especially in brownfield projects. So if it is a completely new building that is being constructed, I think it would be amazing to have this design laid out even beforehand, and that's where AI can help.
Okay, now I got to wrap us up really, really quickly. We'd like to extend a great thank you to all of our panelists. Thank you so much. And to our session sponsor, Influx Data, each of you for joining us. We hope you enjoyed the rest of your event. The next session is AI-driven process optimization, achieving faster turnaround and higher margins. Have a great day.
Thank you.